Hello and welcome. Today we're going to be reviewing AP Calculus AB and BC Units 4 and 5, which together make up applications of differentiation. Unit 4 is contextual applications of differentiation, and Unit 5 is analytical applications of differentiation. We're going to be doing both of those in this video. Let's get started. So let's start with this question. This is a question, basically we're interpreting this statement and trying to find how it relates to differentiation. So essentially we ask for the slope of the line tangent, and we see that at t equals 5 it's equal to 0.1. And we can start to make some conclusions about what that means. Alright, so how we're going to do this is we're going to think about how or what the function is and what is really going on in context, right? This is differentiation in context, not just in terms of a function and finding the numbers. So here, the function w gives the pool's water level in meters after t minutes. So the slope of the line tangent to the graph of w is the rate of change of the pool's water level. At the rate of change of the pool's water level, right? And we're told that at t equals 5. Well, what does t equals 5 mean? Right, let's see. Let's draw a text box here and just try to think about what this means. So essentially, the rate of change of the pool's water level at t equals 5, well, it says after t minutes, so after 5 minutes is equal to 0.1. 0.1 what? Well, the rate of change is going to be the units of w divided by the unit of time, or meters per minute. So here the rate of change of the pool's water level after 5 minutes is 0.1 meters per minute. That is what this statement means. Let's move on. Here we're told that the function d gives the day length in minutes of the nth day of the year in Juneau, Alaska, and we're asked to find a d prime of 10 equals 3. And we're asked, what does that mean? So let's see. Well, the function d gives the day length, so the d prime would be the rate of change of the day length of the 10th day, right? Because we're told the d events of the nth day of the 10th day is 3 is equal to 3, right? And 3 what? Well, we're told that the function d gives the day length in minutes. So in minutes, so the initial function is in minutes. Now the nth day, so it changes per day. So the day length, the rate of change of this day length is going to be 3 minutes per day. Right, so every day it changes by, or at least on the 10th day, and on the 10th day we can write it like this. On the 10th day, the instantaneous rate of change is 3 minutes per day of the change in the day length. That's what this statement means, right? The instantaneous rate of change is 3 minutes per day on the 10th day. Let's keep going. Alright, here we're told that Carlos has taken an initial dose of a prescription medication. The function n gives the amount of medication in milligrams in Carlos's bloodstream after t hours. And we're asked to find m prime of 5 equals -1. Well, we can say the rate of change of the amount of medication, right? Because that is what the function m is. Rate of change is the amount of medication, or the derivative of that, the instantaneous rate of change, at, or say it's 5, so t is 5, so it's after 5 hours, is -1. -1 what? -1, since m is in milligrams, we're going to do milligrams, and the unit of time is hours, so the rate of change of the amount of medication after 5 hours is -1 milligrams per hour. Alright, let's go to this question. This is the last question of this type. Alright, here we're told that P gives the lion population at a certain game reserve T years after the reserve was established. What is the best interpretation for the value of the derivative of P at T equals 6 is equal to 12? Alright, Let's see what we can do with this. Well, the value of the derivative, right, the rate of change, did not mean for that to happen. So, again, the rate of change of p, which is the lion population, of the lion population at t equals 6, right? T is in years, so it's 6 years. The rate of change of the lion population 6 years after the reserve was established is equal to 12. It is 12. 12 what? Well, the unit of p is population or lions, so 12 lions, and the unit of time is in years, so it's going to be 12 lions per year. Let's move on. Alright, so that was it for the questions about context, basically differentiation in context, trying to interpret statements. Now we're going to get into this thing called related rates. Now you might know related rates. Most students extremely hate related rates because it's kind of weird sometimes, but the basic principles of it are kind of simple, right? So what we see here, right, we see the volume of the sphere. That's what we're trying to find, the volume of the sphere. What is the formula for the volume of the sphere? Now on the AP exam, they'll give you this information, but it is 4/3 pi r squared. Or not squared. Pi r cubed, sorry. So that is the volume. And we're asked to find the rate of change of the volume, or dv dt. Now if we want to find dv dt, what do we do, right? What do we do in this situation? Let's think about it. So we just take the derivative of v, so we take the derivative of the other side too. We bring the 3 down here, gets rid of this 3, and we're just left with 4 pi r squared. That is the derivative. Right, now that is that it? Let's see what we have. We have, down here we see it said dt. We did not derive with respect to t, we derived with respect to r. So because of that, we need to multiply this by dr. And this concept is going to show up in all related rates problems, right? You're going to be deriving with a variable that is neither of the variables you're starting with, neither the radius or volume. In this situation, it's going to be time, always. Now we have to see what we can do. So dv dt is equivalent to 4 pi r squared times dr dt. And we're asked to find the rate of change of the volume of the sphere, or dv dt, at that one instant that they're giving us. So at that one instant, right, the radius is 4 meters, so you have 4 pi and then 4 squared, and then you're multiplying that by the rate of change of the volume of the sphere, right? So I'm multiplying that by the rate of change of the radius, the derivative of the radius, which is said to be -1 meter per hour. And it's -1. I'll multiply this together, and we end up with -64 pi. And the units, let's write in this column, -64 pi. And what are the units? Well, so rate of change of the volume of the sphere in that instant, even if we weren't told that it's cubic meters per hour, we could see that since volume is in cubic meters and then times hours, this is going to be meters cubed per hour. That is the rate of change of the volume of the sphere at that one instant. It's extremely important to note that this will not be true for all instants. Right, even if this holds true, this 1 meter per hour holds true, then this radius is going to be constantly changing, and the rate of change of the volume will not always be this one value. But at the instant they're giving us, it will be that one value. So that's it for that question. Let's move on to another question. Let's move on to another question about this. Alright, so here we're told that the radius of the base of the cone is increasing at a rate of 10 meters per second. The height of the cone is fixed at 6 meters, and at a certain instance, the radius is 1 meter. Let's see what we can do here. So first we're going to find the volume of the cone. So the volume of a cone is 1/3 pi r squared h. Now there are a couple things we can do. Right, so we know that height is fixed at 6 meters. So instead of a height here, we put 6. The 6 times the 1/3, that just gives, that all cancels out. That all cancels out. All cancels out to give 2 pi r squared, right? Now, we need to find the rate of change of the volume of the sphere, or the volume of the cone. Now, we take the derivative of both sides, we get, dv dt equals 4 pi r dr dt. I multiply this out, right? Plugging in r as 1 meter and dr dt as 10 meters per second, and we end up with 40, that I did not mean for that to happen. We end up with 40 meters, cubic meters per second as our rate of change of the volume of the cone. Let's keep going. The radius of the sphere is decreasing at a rate of 4 centimeters per second. We're told that at a certain instance the radius is 10 centimeters, and we're asked for the rate of change of the surface area of the sphere at that instant. Let's see what we can do. Well, we can of course write the formula for the surface area of the sphere. Now, the formula for the surface area of the sphere is S equals 4 pi r squared. And you might notice that this is the derivative of the volume of the sphere. And there's a reason for that, because as you increase the radius at a constant rate, what you're really doing is you're adding stuff on the outside, right? You're adding layers, basically. Right? Those layers are what is the surface area. Each one of those layers is a surface area of its own sphere. As you increase the radius, you're just adding layers, you're adding the surface area, and that's why the surface area is the derivative of the volume. But anyway, in this question, we're asked for the rate of change of the surface area. We do ds dt equals 8 pi r dr dt, which equals, we plug in the 10 centimeters and the negative 4 centimeters per second, and we get negative 320 centimeters squared per second as our instantaneous rate of change. Let's move on. Alright, the last problem in the category of related rates, and here it is. The side length of a square is increasing at a rate of 15 millimeters per second. At a certain instant, the side length is 22 millimeters, and we're asked for the rate of change of the area of the square at that instant. Well, the area of the square is simply the side length squared. So dA dt, the rate of change, is just going to be 2s ds dt, which is going to be plus 15 millimeters per second times 22 millimeters times 2, or let's see, you probably get a calculator right here, but it's going to be 660 square millimeters per second. Alright, let's move on. The next category here is Hopitals Rule. Right, Hopitals Rule occurs when you have an indeterminate form. So there are two indeterminate forms, or really, you can make more than two, but they're really two basic ones. There's 0 over 0, and there's infinity over infinity. Now with this form right here, you can make more variations like negative infinity over infinity, or infinity over negative infinity, like all that kind of stuff, but it really does not matter. It's the same concept where simply both the numerator and the denominator each go to infinity, or both the numerator and the denominator go to 0. Right, so that is what the indeterminate form is. And L'Hopitals rule states that if you have a limit of f of x over g of x, and direct substitution gives you a 0 over 0 or an infinity over infinity form, then this limit right here, then this is going to be equal to the limit of f prime of x over g prime of x, right? And now one thing that's very important to notice is that if you put this second limit and it still doesn't work, you can do it again. You can make f double prime of x over g double prime of x. But you can go on and on and on and on forever, right? But this is the basic form of L'Hopitals rule. This is the form we're going to be using. So let's now get to the problem itself. So in the problem, we're asked to find the limit of the limit as x approaches 0 of tangent of x over 3x tan x. Now we plug in this 0 right here, and then we get tan x as 0 over 3x, 0 plus 0. It's going to give us a 0 over 0 form. Now when you're writing on pre-response question, you're trying to justify using L'Hopitals rule, because you do have to justify it. Make sure you never say that this limit is equal to 0 over 0, or equal to infinity over infinity, because that's not true. It's an indeterminate form, so you don't know what it's equal to. That's the whole point. So in writing a justification for this on a pre-response question, you could say something like, direct substitution yields a 0 over 0 indeterminate form, and then we apply L'Hopitals rule. But here, we're going to apply L'Hopitals rule. We take the derivative of this, which is going to be secant squared of x, and then the denominator is going to be 3 plus the secant squared of x. And then we plug in 0. So secant squared of x, secant squared of 0 is going to be 1 over 3 plus 1. So this is just going to be 1 over 4. Let's keep going. Alright. And another question. And we're just going to plug in, we're going to try direct substitution again. We end up with e minus e over 1 minus 1, which I shouldn't write it like an equal sign. I should just say something like that, right? It's not equal to the 0 over 0. It is simply yields that form when you try direct substitution, which just means that direct substitution is not the right way to go for that question, even though it should be the first thing you always try for a limit. So we take the derivative. This goes away, this goes away, and what we're left with is we use the product rule in the numerator to get e to the x plus x e to the x over 2x, and that ends up being e plus e over 2, also known as just e, the exponential. Keep going. Alright, here we are now. As always, we try direct substitution. 1 minus 1. The natural log of 1 is 0. 0 over 0 is not equal to, remember, but it does yield that form. So we try L'Hopitals rule again. Actually, should not cross out the negative sign. Kind of report it. So we get negative 2x, and then the derivative of ln x is 1 over x. So basically, we bring the x to the numerator, and we get negative 2x squared. We plug in 1 into there, and we end up with simply negative 2 as our answer. Let's move on to the last question of this topic of L'Hopitals rule. Here we are. We're told that we're asked to find the limit of sine x over 5x plus 3 sine x as x approaches 0. We plug in 0 again, and we end up with 0 over 0 plus 0. right, yields this now infamous, I guess, form. But we try Hopitals Rule and we get cosine of x over 5 plus 3 cosine of x. And then we plug in the 0 and we get 1 over 5 plus 3. So our answer is 1 over 8. That is it for that category. Let's move on to our next category, which is the mean value theorem. Now, the mean value theorem is a special theorem that says if you have a function, right? Let's draw a sample function. If you have a sample function like that, and you take this line right here, right? Now, say this line right here has slope c, right? The slope of that line is c, so the average rate of change is c. Now, the mean value theorem states that if this function, right, let's call the function f of x, if the function f of x is continuous and differentiable from x equals a to x equals b, right, so in this interval, if it's differentiable, and the rate of change is c, then somewhere along this line, along this curve, there will be somewhere where the derivative is c. Right, so if we look at it here, we can see one place right here, see another place right here. It doesn't have to be in two places, it can only be in one sometimes. But this is the mean value theorem. If it's both continuous and differentiable, then you can draw these lines, then you know that there's going to be somewhere on here where the rate of change is equal to the average rate of change. Now, when you're doing a free response question, you're trying to justify this, what you say is, first you say that f of x is both continuous and differentiable, right? That's your first thing. Then you have to actually find the rate of change, right? Now, once you find the rate of change, then you know that there's going to be some c, right? There's going to be some number on this interval from a to b where that number, the derivative of that function at that x is the same as this total average rate of change. Now, there is a variation of this, which you don't really have to know, but it's good to know. It's called Rolle's theorem, and it's essentially the same thing, except the mean value theorem has an average rate of change, and Rolle's theorem is only applied when you start and end at the same point. So, when you start and end at the same point, that's the only time it applies. Right? Only when you start on the same point. You don't really have to memorize that one, just use the mean value theorem and you'll be fine. But with that said, let us actually do the problem at hand. Alright. Now, we are told that the g of x equals square root of 2x minus 4, and c is the number that satisfies the mean value theorem on 2 is less than or equal to x less than or equal to 10. So first we find the average rate of change. We plug in 2, we get square root of 4 minus 4, or 0. Plug in 10, we get the square root of 20 minus 4, the square root of 16, which is 4. So the rate of change is 4 minus 0 over 10 minus 2, or 1/2. So 1/2. So what we're really looking for is some c where the derivative is equal to that 1/2. So what we're going to do is we're going to find that derivative. So we can rewrite the square root of 2x minus 4 as 2x to the 1/2. Take the derivative, we get 1/2 times this times 2. If you don't know how we did this, be sure to check out the other videos on the chain rules. So then this goes away, and we're just left with this as the derivative. And that's supposed to equal 1/2 at some point. Alright, now we can, so essentially we can set this equal to 1/2. And then we can square both sides, and we get 2x minus 4 to the negative 1 equals 1/4. And then we take the reciprocal of both sides, That gets rid of this negative 1, and that gets rid of this 4. So basically, we're just left with this. Oops. No, did not mean to do that. Basically, we're just left with that. Right, 2x minus 4 equals 4. Not very hard at this point. 2x equals 8, x equals 4. So our answer here is that the c at which x x satisfies the mean value theorem is going to be x equals 4. Next question, let f of x equals the square root of x plus 9, and let c be the number that satisfies the mean value theorem for f on the interval 0, 16. Well, we do the same thing as last time. We simply plug in the numbers, and we get 3, 2, 5 for 0 to 16. So it's going to end up being 5 minus 3 over 16 minus 0, or 1/8 as the rate of change. So basically 1/8, I'm going to write that over here, 1/8. And we're going to take the derivative. So x plus 9, the square root of x plus 9 is x plus 9 to the 1/2. The derivative is going to be 1/2 x plus 9 to the negative 1/2. That's going to equal 1/8. We multiply by 2 on both sides, making this a 4th. We square both sides, making this 1/16, and then we take the reciprocal of both sides, making this just 16, and then x is going to be equal to 7. Let's move on. Alright, let h of x equals x cubed minus 9x squared plus 7x, and let c be the number that satisfies the mean value theorem for h on the interval -3 less than or equal to x less than or equal to 6. We plug in 3 and 6, and -3 and 6. I'm guessing you know the drill by now. And we end up with -27 minus 81 plus 21, or no, minus 21. Very extremely negative, so it's going to end up being negative 129. Negative 129 there. And then you plug into the other one, you get 216 minus, what is that, 324, and then you add back 42, and you're going to end up with negative 66. Now, on this question, you most likely have a calculator, right? I don't have a calculator right now, so I'm just doing it in my head. Yeah. You take the difference of these two, right? So the negative 66 minus the negative 129, and you're going to end up with 63. But 63 over the difference of 9 is going to be 7. And then that's going to be equal to the derivative. So let's take the derivative. 3x squared minus 18x plus 7 equals 7. What a coincidence, these two cancel out. This is equal to 0. Now we have two solutions here. We have both 0, and then we have 6. Right? So both of these could work theoretically, except that 6 is an endpoint, and you cannot take the derivative of an endpoint on an interval because, like, if you had a function that looks like this, but you can't take the derivative on this endpoint right here because you don't know how it could have gone. It could have gone like that, or like that, or like that, or like you just don't know. That's why you don't use the endpoint. You use the other one that's not an endpoint, which is 0. Let's move on. All right, this is the last question on the mean value theorem, and we have f of x equals negative, or the square root of 4x minus 3 over 1 to 3. Yes, you know the drill right now. We go from 1 to 3, 1 to 3 in the interval as well, so our change is 1. And then the derivative is going to be, let's the 1/2 times 4x minus 3 to the negative 1/2 times the 4. So then equal. So then this is just going to be on this side. It's going to be 2, and then we divide the 2 out, and we get 1/2. We square it. We take the reciprocal, and we end up with equals 4. So 4x equals 7, and x is equal to 7/4. And that's it for the mean value theorem. Go on to the next topic we're going to talk about, which are critical points. The critical points are essentially where the derivative is 0. And we use critical points because they can tell us where local minima and maxima are, right? So if we have something that looks like this, right? The maxima is right there, right? When you have a derivative of 0, right? So that's a critical point, right? The minima is down here. Now, a way you can find the maxima and minima is that for a minima, it's going from negative derivative to positive derivative, and a maxima is going from positive derivative to a negative derivative. That was not a good process then. A positive derivative to a negative derivative. But that's not what we're going to be talking about here. We're just going to be finding the critical points, right? So we take the derivative, obviously, and we end up with 2x plus 2 times e to the x squared plus 2x. There's no way to get the second part right here to be 0, so we just use the first part. 2x plus 2 equals 0, so x is going to equal -1. That is our only critical point. Let's try another problem. Alright, here we have e to the x times x minus 1 to the -1. Take the derivative, and we end up with the x times what? Times x minus 1 to the -1. And then the other term would be minus x minus 1 to the -2. So this one right here is never going to be 0. The other one is just going to be, what is this, like, the other term is going to be 1 over x minus 1 minus 1 over x minus 1 squared. So essentially, we just want those two to be equal. So we end up with x equals 2. X equals 2. All right. That's a critical point for this function. Let's keep going. You know the drill. So now here we have something interesting. Negative sine x, right? Negative sine x has a domain from -1 to +1. But yet we have a +2. And what, so yeah, we have a +2, so the range for sine x is -1 to +1. So the range for this function is just going to be 1, 2, 3. So it's never going to go to 0. So they have no critical points, or CRP. No, you cannot see that, can you? No critical points. You can see that. No critical points. Alright, let's move on. Question number 21. Similar question. We're going to do the same thing. So the derivative here. The derivative here is going to be this. I might be skipping a couple steps here, but of course this is just taking the derivative, right? If you can pause the video if you want. You can always pause the video if you need to and just work it out on your own, right? It takes a bit longer. This part, not 0. The other part is going to be this. Now we multiply the x minus 3 squared to both sides, and we get that 2 times x minus 3 is equal to 1. So that means that x minus 3 is going to be 1/2. So x is going to be 3.5 or 7/2. That's our answer. Alright, move on. Now we're done with the questions about critical points. Now we're going to do the thing called the second derivative test. Second derivative test is very useful because it helps you find if something's a local minimum or a maximum when the derivative at a point is 0. So when you have a critical point and you don't know the behavior around the critical point, if you did know what was going on around the critical point, you could find it, right? Because it's a negative to positive for minima and positive to negative for maximum. But if you don't know that, you can find it. You can find if it's a minimum or maximum using the second derivative. Yeah. All right. Second derivative test is a bit backwards, right? So if your first derivative is 0 and your second derivative is positive, it's a minimum. Minimum if f prime of x greater than 1. Greater than 0. And it's a maximum if f prime of x is less than 0. Now this might seem a bit backwards, right? Like, why is this happening? But let me give you an explanation. So, you remember when we drew something like this? That's a horrible graph. When we drew something like this, still a horrible graph. Alright. Just going to be sitting here trying to draw a graph for who knows long. Alright. That was a pretty crappy graph. And it only has a minimum, but we'll make it do. Right, so here, at this point, we have a critical point. Here we have a negative. Here we have a positive. So essentially, we're going from negative to 0 to positive. So the derivative is increasing. So the second derivative is positive. So if the second derivative is positive, we're going to go from negative to positive, or minus to plus for the first derivative. So if the second derivative is positive, then you're going to end up here with a minimum because of what's going on right here. The same thing happens for a maximum. You go from the positive derivative and the derivative shrinks to become negative. And that's how you get the bottom part. Right, anyway, so now we're going to do this using what we know in the question. The first derivative is 0. No surprise. If you're going to use the second derivative test, the first derivative has to be 0. And the second derivative is positive, so it's going to be a minimum point. Right, so our answer here is A. Keep going. Alright, let's look at this question. The first derivative is 0. The second derivative is also 0. We didn't discuss what happens if the second derivative is also 0. And that's because there's not really anything to discuss. Right? Since if your derivative is not changing, if the second derivative is 0, then your derivative is not changing. So just like a flat line. Right? Or maybe not like a flat line. Right? But it might be something like this. Right? Either way, it's not going... Most likely it's not going to be a minimum or a maximum, but you don't know. And therefore the answer is C. There's not enough information, so you just don't know. Right? There might be a third derivative test out there to help you, but you don't know for the time being, and you cannot find it using the information you have. Right, let's look at this question. First derivative is 0, no surprise. Second derivative is negative. That means that the point must be a maximum point. Keep going. We know that the first derivative is 0, the second derivative is positive, so we're going to end up with a minimum point, and that is it for these questions on the second derivative test. We're going to go now to our last topic, which is optimization. Optimization is another topic along with related rates, which students usually don't like, simply because it's hard to do, and sometimes it doesn't just use calculus, but it also uses a bunch of stuff about like area and surface area, which is mostly related rates. And here we just have some geometry and trying to set things equal to each other, and it's just a mess sometimes. And I do kind of understand that, but if we do this in a set process, then we'll be able to do it very easily. So let's see what we can do. So here we have an open-topped glass aquarium, right? So it's going to have the square base at the bottom, and then 4 separate sides, right? No top, 4 separate sides, and it's designed to hold 13.5 cubic feet of water. we're trying to find the minimum exterior surface area of the aquarium. So the 13.5 is going to be essentially the length squared, right? The length is the base, so the length squared times the height. Which means that we know that the height is the length squared over, sorry, not the length squared. It's going to be 13.5 over the length squared. 13.5 over the length squared. And we're going to make a new slide to get some more space, because these problems do require lots of space. Now we have that the height equals the 13.5 over the length squared. And now what we're going to do is we're going to try to find the minimum surface area. So the surface area we can quantify as L squared at the bottom plus 4 sides times H times L. Right, so essentially that is our surface area. And now, since we know that H is 13.5 over L squared, we know that the surface area here is L squared plus 4 times 13.5 is 54. 54L over L squared. So we just get rid of this L, we get rid of the squared. And that is our surface area right there. Now we want the minimum, so we take the derivative, because that gives us our rate of change, right? That's how you do these problems. Right, so then you get 2L minus 54 over L, just equals 0. And then, so you bring the 54 on the other side, and then you multiply by the L. You divide by 2, and then you end up with the square root of 27, and the negative square root of 27. Now, of course, these are lengths, so you cannot have negatives, so it doesn't work. Square root of 27 is, of course, 3 root 3. So 3 root 3 is our length. We plug it into this equation here, and we get that the minimum surface area is 27 plus, well, that looks to be 18 over the square root of 3. So 27 plus 18 over the square root of 3, which is quite a mouthful, but still. Right, so these questions, these optimization questions, have a set process. And essentially, you have 2 separate measurements that you're trying to find, right? One measurement you can find, and one measurement is in terms of multiple different variables. So you use the first measurement to express all the variables in terms of one singular variable. You take the second measurement and then split it to make it that one singular measurement, and then you take the derivative, you find the critical points, and you find the minimum or maximum, whichever one is asked. So that's what we did here, right? We found 13.5 equals L squared over H. We quantified H in terms of the L. We substituted L in right here at the bottom, and then we solved for the derivative using that, and we found the critical point. We plugged in the critical point, and that's how we solved the problem. All right, let's do this question now. What is the maximum vertical distance between the lines y equals x plus 2 and the parabola y equals x squared for -1 less than or equal to x less than or equal to 2? So we can essentially set these two equal to each other. X plus 2 equals x squared. And then we do x squared minus x minus 2 equals 0. If you noticed it, then you can factor this, make it a bit more simple, something that's probably going to come up. So x minus 2 times x plus 1 is going to equal 0. We're trying to find the maximum vertical distance between the lines. So the maximum vertical distance between the lines for -1 is less than or equal to x is less than or equal to 2. Here, do this for a second. So we're trying to find the difference, right? So this difference, actually, let me put this back. We're trying to find the difference. So the difference is x squared minus this, or just this part. And we're trying to find that maximum for the interval -1 less than or equal to x less than or equal to 2. Now we just take the derivative of this function we found, right? The x squared minus x minus 2, the derivative, and we end up with 2x minus 1, which equals 0, so x is 1/2. It's 1/2. And then when we plug that in there, we see that that distance is going to be, let's see, it's going to be 1/4 versus 2.5, so it's going to be 2.25. That is our maximum vertical distance. Now, before we move on, I just want to point out one really important, interesting thing that you can see here, which is that 1/2 is right in between the endpoints. And the endpoints are the roots of this quadratic function, meaning that x equals 1/2 is the vertex of this parabola. The vertex of this parabola is going to be the maximum vertical distance. You could have found this by thinking that, well, you have this part here, and you have this part here, and you're going to multiply them, and if you're going to multiply two things, they're always going to be the biggest when they're the closest. So if you plug in 1/2, you get negative 1.5 and 1.5. Since we're trying to find an absolute value, just going to be 1.5 times 1.5. That gives us our maximum vertical distance. Just an interesting thing I thought I'd throw out there. But let's move on. Function f is defined as f of x equals 2x plus 3. We're trying to find the x-coordinate of the point on the function's graph that is closest to the origin. Well, so a point, right, on this line is essentially just going, that's a huge point. A point on this line is essentially just going to be x times 2x plus 3, which means that the distance is going to be x squared plus 2x plus 3 squared. I'm not sure of that. Right? Now we can calculate this out, and we find that we get the square root of 5x squared plus 12x plus 9 right? So 5x squared plus 12x plus, let's make another slide to make this easier to read. So we end up with 5x squared plus 12x plus 9. And when you find the derivative of this, so we end up with 1/2 times 5x plus 12x plus 9 to the negative 1/2 times the 10x plus 12. And now this might look complicated, but we know one thing, and that is that we don't have to care about this right now. The reason we have to care about that is because this is a negative 1/2, right? So the only way this can never, this part, like this whole part, is never going to be 0, right? Because that would mean that this part without this would have to be infinity, and that doesn't work. It doesn't work that way. So knowing that it has to be that this part that goes to 0, then we get that x is going to be negative 6 over 5. X is negative 6 over 5. We were asked for the x-coordinate, and this is our answer. Right, let's move on to the last question. At what argument x is the maximum vertical distance between the curves f of x equals 2 cos x and g of x equals sine 2x for x in negative pi over 2 to pi over 4 achieved? So we're trying to find the maximum vertical distance, so we subtract them. Maximum vertical distance, 2 cosine of x minus sine 2 cos 2x, and then we take the derivative. Negative 2 sine x minus 2 cos 2x. Now, since this is a distance, right, it's a distance, right, not like a displacement or anything, we can just make this a plus, 2 pluses. We can flip the sign, right? So this is just going to be 2 sine x plus 2 cos 2x, and it's going to equal 0. So we put them on separate sides. Sorry, put them on separate sides. We get rid of the 2's. Now we have negative sine x equals cosine of 2x, and we have to try to figure out where is that satisfied, right? What number is that satisfied at? And we can think about this, right? Because we know that cosine of 2x is going to be cosine squared of x minus sine squared of x, also known as 1 minus 2 sine squared x, which means that we can put all the terms on one side, and we get that 2 sine squared x minus sine x minus 1 equals 0. And we have to find something that satisfies this, but there's really not much to, it doesn't seem like there should be too much, right? Because if we plug in sine x equals 1, then this should be satisfied. Now the problem here is that we can't plug in sine x equals 1, because we're only allowed to use negative pi over 2 to pi over 4. And sine x equals 1 would be x equals pi over 2. Now, since we know that one of the roots is going to be 1, the other root, since the product of the roots is going to be negative 1/2, the sum is going to be 1/2, since we know by Vieta's formulas. We know that the other one that sine x can be is negative 1/2, right? Now, of course, if what I'm saying about these quadratics, the Vieta's formulas seems unfamiliar to you, please look it up. It's an extremely important topic. Essentially, the sum of the roots is negative b over a in a quadratic, and the product of the roots is c over a. It's very useful. You can use it, but for the purposes of this question, it's not that important. But we do find that sine x is going to equal negative 1/2, which means that x itself is going to equal negative pi over 6. So x is going to be negative pi over 6, and that is our answer for the argument x at the maximum vertical distance. They didn't ask us for the vertical distance, they asked us for the x, and the x is negative pi over 6. Well, that is it for this video. I hope you liked it. I hope you found it informative, and if you did, please like and subscribe. Until next time, I'll see you then.